Hi everyone. In this video, we're going to go through the practice SAC questions. So just remember, this isn't necessarily how your SAC is going to look, but it's good practice or good revision for you to do beforehand. So the big question we have for this revision sheet is there enough information to find the equation of a polynomial function? So I'm going to read through the introduction just because I think, even though I know you can read, I can elaborate on some things that might not make sense. So often to solve a mathematical problem, it is necessary to find a particular line or curve which goes through a given set of points. How many points are needed so that only one curve can be found that goes through the given points? If the number of points is such that only one curve passes through them, then this information uniquely determines the curve and its equation. So the information necessary to determine the equation of a curve may be in the form of the coordinates of a number of points on the curve or the gradient at a particular value of x. So just remember that you need points on your curve or you need the gradient at a particular value of x. So that's where your derivative comes in. So for a quadratic function, y equals ax squared plus bx plus c, three independent pieces of information are needed. So that means you need either 3 points or 2 points and a gradient. So 3 independent pieces of information are needed in order to find the values of a, b, and c. If you didn't have 3 independent pieces, you wouldn't know what a, b, and c are. Okay, so you wouldn't have what we call a unique curve. I might just underline that. Okay, so also for a cubic function, so if we had y equals ax cubed plus bx squared plus cx plus d, you need 4 independent pieces of information. So you need to find a, b, c, and d. So you could have 4 coordinates, 3 coordinates, and the gradient. If you didn't have 4 independent pieces, you wouldn't have A, B, C, and D. So what we're going to do in this worksheet is explore both quadratics and cubics and what that actually means by how much information you have and what the polynomial and what the graph actually looks like. So therefore, if we have 3 points or 3 pieces of information, then we will be able to find one and only one quadratic function that will go through these points. So remember, 3 points or 3 pieces of information, we've got enough information to determine our quadratic. Now, for the same 3 points or 3 pieces of information, we'd also be able to find a whole family of cubic functions that would fit the data, but we wouldn't be able to find one unique cubic function. So we'd be able to find a whole bunch of cubic functions that kind of look the same but were perhaps stretched or transformed in some way, but we wouldn't know A, B, C, and D. We would have one value left that we don't know the value of, and that's why it's called the family, a family of cubic functions. Okay, so we have only 3 bits of information, so we don't have a unique cubic function, we have a family of cubic functions. So in this task, we'll investigate the possibility of finding either a unique or family of quadratic or cubic functions that fit or model the given information. All right, so question 1. All the answers have been done already, so I don't have to worry about my messy handwriting. All right, so the following information is given and a polynomial function is to be found, which will model the data. So remember, a polynomial isn't necessarily a quadratic. It could be a cubic, could be a quartic, and so on. Okay, so what we have is we've got 1 bit of information, 2 pieces of information, and 3 pieces of information. So what we have is 2 points, okay, which are here, and they're our x-intercepts. The reason why we know they're the x-intercepts is because we know f of x is equal to 0. So f of -1, so that's your x coordinate, is equal to 0. So -1, 0 is one x coordinate, sorry, x intercept, and 4, 0 is your other x-intercept. Now, the other bit of information, f-2, so that means our gradient function at x equals 2 is equal to 0. So your gradient is equal to 0 at x equals 2. All right, so I'm going to write that over here. So f-2 equals 0. This means that your gradient is 0 at x equals 2. Now, when you've got a gradient that is 0, it could be a turning point or a stationary point. So we need a little bit more information to determine, well, what is it? So that's what we've got here, and it's already been put in a border for you. So when your derivative is less than 0 for x is greater than 2. So what we've got here on our graph, we've got our x-intercepts at -1 and 4. And it's saying that our gradient is less than 0 for x is greater than 2. So here's our turning point. So our gradient has to be decreasing. So it's negative. It's less than 0 when x is greater than 2. So x is greater than 2 all the way down this way. All right, so that's why it's going down. And your gradient is greater than 0, or it's positive when x is less than 2. So there it is. And you could draw a sine diagram, which we've got here as well. So your turning point at x equals 2 is f-2 equals 0. So there's your curve. All right. What is the nature of the stationary point? So your stationary point is when your gradient is equal to 0, okay? It's a local maximum because it's our maximum point, all right? And it's a negative parabola, so negative parabolas always have, sorry, it's not necessarily a parabola, but it is a negative curve, so it's a local maximum. So it's the high point, the maximum point. If it was the other way around, if it was reflected along the x-axis, it would be a local minimum. Sorry, it's not a quadratic, and we're going to answer why in question 3. So part 3, explain why a quadratic function cannot model this data. So when you think about quadratics, they are symmetrical. All right, so there's if you have your two x-intercepts, so here -1 and 2, your turning point is always halfway between them. So halfway between -1 and 4, so if we were to add them together and divide by 2, so -1 plus 4 is 3, 3 divided by 2 is 3 on 2, or 1.5. All right, that's where your turning point should be, but for this graph, it's at x equals 2. So that's why a quadratic function cannot model this data. All right, turning over the page. So question B, part 1. Change the position of the stationary point so that the data could be modeled by a quadratic function. All right, so before it wasn't a quadratic because our turning point wasn't halfway between our x-intercepts. So as I said before, and I worked it out for you, how halfway between your x-intercepts, you add them together and divide by 2, which is what is done here. So we get 3 over 2. So your maximum has to occur at 3 over 2. Sorry, I didn't even finish talking about the question. The stationary point is to remain the same type. What could be the location of this stationary point? So we know it has to occur at x equals 3 on 2, but we don't know what the y value is. It could be anything, all right? So it does say what could be, not what is. So that's why we could have multiple answers. So your answer to this question could differ to the person next to you, could differ to the person next to you. So you can see in the part 2, give the equation of 3 of the family of possible curves and sketch them on the same set of axes. Describe how they differ from one another. So you can see the blue curve, the green curve, and the red curve all have the x coordinate 3 on 2. All right, so they all have their x coordinate of their turning point at 3 on 2. But we have different corresponding y values. All right, do you see how they all differ? So what we have here in factorized form, we've got the turning, not the turning points, the x-intercepts, or the factors, x plus 1 and x minus 4. You can see they're consistent, but the value of a is changing each time. So for this one here, the first one, we've got a is equal to -1, a is equal to 2, -2, sorry, a is equal to -3. So when we substitute those values into our quadratics, we get these three different ones here. All right, so you can see also on this side, so they've been color coordinated here. Y1, which is when a is equal to -1, we get the blue curve. Y2, the green curve, when a is equal to -2, and then the red is when a is equal to -3. And you know, that's your dilation factor. So what we've got written just underneath here is the factorized form is the easiest for given information. They differ by dilation factor from the x-axis. So you've got the same parabola, it's just being dilated by a different factor each time. All right, let's go on to question C. Now, to be able to determine the equation of a unique quadratic, that is in the form fx equals ax squared, f of x equals ax squared plus bx plus c, three pieces of information are needed. So one more piece of information must be added to the above to uniquely define the parabola. So in the previous question, in part B, we found a family of quadratics. So they differed just in their dilation factor. So what we're going to do here is find a unique equation for a parabola. So it could be either a point or a gradient for a particular value of x. So part 1, choose the coordinates of another point that the parabola must go through. Sketch the graph of the quadratic that satisfies this information. Clearly show these points on the sketch. All right, so I'm just going to read through the solutions. So for another point, when y is greater than 0, so y is greater than 0 when x is between -1 and 4. Okay, so you can see here from -1 to 4, y is greater than 0, or y is less than 0 when we're less than -1, x equals -1, or greater than y equals 4. So points 1, 0, 4, 0, so we already had those two, and just a selected point 2, 3. All right, so we've just chosen that point there, 2, 3. So you could get that point, I'm just trying to think. So for a local maximum, new point could be 2, 3. Find equation by either simultaneous equations or let f of x equal x plus 1, x minus 4. So what it means by simultaneous equations is you could have it in polynomial form and substitute those values of 3. So 3 equations, one substituting in -1, 0, one substituting in 4, 0, and one substituting in 2, 3. But because we know that -1, 0, and 4, 0 are our x-intercepts, we can use the factorized form, which is a little bit easier. But if you didn't have these, you would have to use 3 equations in polynomial form. So what I mean by polynomial form is ax squared plus bx plus c, and then you'll just substitute in the 3 points. So 1, 2, and 3, but we don't need to do that because our 2 points are our x-intercepts. Okay, so when we substitute in 2, 3, we get the value of a to be -1/2, so you can factorize that out, get it in, not factorize, expand that to get it in expanded form. Now remember, for your SAC, you can use your calculator. All right, so a lot of this, you would be writing this down, but you can easily just press expand on your calculator and expand it on your calculator, or write the 3 equations and solve on your calculator. All right, and we sketch the graph. So there's a graph there. So when we sketched it, just make sure you got the correct turning point. All right, and the y-intercept. So the easiest way to get those would be just to graph it on your calculator, or if you didn't have a calculator, which you're going to have, but if you didn't, all right, we can see the constant here would be our y-intercept, and then your turning point we know has to be at 3 on 2 because it's halfway between -1 and 4. So you just substitute 3 on 2 into your function and you should get 25 on 8. All right, let's move on. So part 2, this time choose a value of the gradient at a chosen x value and use this information to find the equation of the quadratic that will satisfy this information. Hence, sketch the graph showing all important features. So it does say choose a value of the gradient at a chosen x value. So it's up to, this information is given to us. All right, so we know those 3 bits of information. What else have they chosen? Sorry. Okay, so local maximum, All right, so we've substituted in the 2 points. All right, so we've got 2 equations when substituting in -1, 0 and 4, 0. So there's equation 1 and equation 2. And then our third equation, we can find the derivative. Okay, so 2ax plus b. And the derivative at x equals 1 is 2. Oh, okay. So what I think has happened here, sorry, I'm a little bit lost. So it said choose a value of x. Okay, so chosen value of x, so you can choose whatever you like. All right, so in this example, it's just chosen x equals 1. So when x equals 1, your gradient is 2. So we're left with, this is our third equation. So basically what we're finding here is just another unique parabola. So we've got those 3 equations, and as I said before, you can just solve them on your CAS calculator. So we get a equals -2, b equals 6, and c equals 8. You can solve them by hand. Might take a little bit of time, but don't look that complicated. So because our polynomial is in this form here, all right, in expanded form or polynomial form, it's just a matter of substituting the value of a, b, and c, as you can see here, it's an arrow, back into the equation. So we've got f of x equals -2x squared plus 6x plus 8. And there's our graph. So again, your constant giving you your y-intercept, and your turning point changes because obviously we're substituting in different values. So we're looking at a family of functions, a family of parabolas that go through the same x-intercepts and have the same x-coordinate of the turning point, but we're just looking at exploring different parabolas. All right, let's move on. Lots of scribbling on the page. All right, so question 2, a family of cubic functions with the rule y equals ax cubed plus bx squared plus cx plus d can be found to model the following data. All right, so there's a bit of writing on here, so I'll just show you. We've got 1, 2, 3 bits of information. So what we have here is the first point. Is it written down anywhere? No. So you've got the point -1, 0. Okay, so that's an x-intercept. You've got the point 4, 0, just like before. And we've got the gradient. So gradient, I should be using f dash x equals 0 at x equals 2. All right, so that means your curve is going to have a turning point or a stationary point. So what this next bit of information is telling us is, well, what is actually happening at x equals 2. So your gradient function is less than 0 when x is less than p, where p is less than -1. All right, so what we've got just here is a sign diagram. So that's going to help us decide, well, what type of turning point or stationary point is happening at x equals 2. Now your gradient is also less than 0 when x is greater than 2. Okay, so when we've got p here and 2 here, so your gradient is less than 0. So you can see on the sign diagram we're below when x is less than p and below when x is greater than 2. And then the last bit of information, your gradient is greater than 0 when when x is between p and 2. So you can see here. So what is actually happening at p? All right, so this is actually, I'm just doing two things at once, I've just realized. So at point P, if I show the graph, let's scroll down. So you can see here is point P is a local minimum because your gradient is decreasing until we hit P, and then it's increasing until it gets to 2. So it's going to keep increasing until it gets to 2. Now, let me just see if we've got, and when x is greater than 2, it's decreasing again, which I've already drawn on my sign diagram. So we're going down. All right, so we've got our 2 points, our x-intercepts at 4 and 1. We don't know what this point is, okay, but we know that at P we've got a turning point, so we've got to go up, and P we don't know what the value is, okay. So when we're plotting this, the important information is the 2 x-intercepts, so -1, 0, 4, 0. The gradient is 0 at x equals 2, so you can see here. We don't know what the corresponding y value is because we don't know what all the values of the cubic are, and we've also got a turning point at x equals p. All right, so there's our cubic. All right, so we don't have all the information, but that's the cubic in terms of what information we do have. All right, part 3, let a equal -1 and use the above information to find the equation of a cubic function that would fit this data. Sketch the graph of this cubic showing all important features. All right, so we know that a is equal to -1. So usually we would have our cubic function, f of x equals ax cubed plus bx squared plus cx plus d. But we know that a is equal to -1, so you can see here our coefficient of x cubed is already -1. So here is our first equation. Our second equation comes when we substitute in the point -1, 0. Oh, it's labelled it as 1, so it's labelled that as equation 1. Substituting in the point 4, 0, there's equation 2. And our gradient function, we know that at x equals 2, it's equal to 0. So there's number 3. And then you can just solve on CAS. I don't think we needed that first one, although we probably could have used it. Let me just, maybe not. So when we solve on CAS, we already know a is equal to -1. So we get b equals -1, c equals 16, and d equals 16 also. So when we substitute it in, we get this. Now plotting the graph, just do it on your calculator, but if you needed to know what the points are, all right, I'm just trying to think of how we can do that too. yeah, I think the only way is to find the gradient. So substituting these back in, sorry, not substituting them back in. So using this function, finding the derivative, and then letting that derivative equal 0 will give you this value here and this value here. But yeah, something like this, just we should do as much as you can on the calculator. Just make sure you show you're working like this. Okay, there's nothing wrong with solving it on your CAS, but showing where those 3 equations have come from. All right, part 4. Find the equations of 2 more members of the family of cubics and sketch these together with one from part 3 on the same pair of axes. How are the 3 related? All right, so we've still got our x-intercepts at, so we're going to keep -4, -1, and 4. So you can see in factorized form, we're going to have this. I didn't point that out before, that your x-intercept was at -4. So we're going to keep it in factorized form. So x plus 4, x plus 1, and x minus 4. And we're just going to have different values of a. All right, and we know that a is just going to dilate the graph from the x-axis. So you can see the 3 different graphs here. So we've got, where are they written? Oh, here. So F1, is that what we had before? I can't even think. So here's F2 and F3. So we're just looking at, oh, we only had to do 2. So F2, F3 are our 2 new functions, and you can see just putting in different values of a. So a equals 2 and a equals 3. Okay, the negative was already there. And then the original graph, the blue one, is drawn on there as well. So you could have any value of a there. All right, part 3. Now look at the data used in question 1b, part I. Investigate what happens if the point -1, 0 is replaced by the point 1, 3, and a quadratic is used to model the data. Find the equation of any quadratic that fits the information and explain why it is now possible to find a unique quadratic where in 1bi it was not. Okay, so just looking at the information from 1b, part I, so we had the point 4, 0, we had the gradient is 0 at x equals 3 on 2, and we know that's a local maximum. And now instead of the point, what was it, -1, 0, we now know the point 1, 3 is on the curve. So what we have is 3 equations. So you can see here, 1, 2, and 3, just substituting in the 3 bits of information. All right, so if we do solve on the calculator, we get this, and then we're just substituting it back into the equation to get this. So remember, in polynomial form, it's here. So once you get a, b, and c on your calculator, you can just substitute them back in your function. All right, so your explanation as to why it's not possible. So earlier we had 2 x-intercepts giving the same type of information. That is what happens when y is equal to 0. 1, 3 is not an x-intercept, so it gives more information. All right, it gives another y value. So it provides, you know, I guess we know the quadratic had to go through those x-intercepts, but we didn't know what the rest of it looked like. So having 1, 3 on the curve just helped us see, well, what shape is it going to take? All right, part B, part 1. In part 1b, we looked at the turning point and x-intercepts of a quadratic. Now investigate a cubic function and its turning points. So take the data from 1b, part I again, and see what happens when the data is modeled with a cubic polynomial, y equals ax cubed plus bx squared plus cx plus d. Attempt to find a family of curves using simultaneous equations. What conclusion could you use? Sorry, what conclusion could you draw from this result at this stage? So we've got, excuse me, our x-intercepts, and the gradient is 0 at x equals 3 on 2. Here is polynomial form of your function, and there is the derivative f dash x. So what we have here is we're substituting in -1, 0, 4, 0, and then your gradient is equal to 0, x equals 3 on 2. So solving this into the calculator, we don't get unique answers for A, B, C, and D. So no unique solution at this stage. We need more information. So if we had so this is the turning point y value, we get a quadratic, not a cubic. Okay, so we need a little bit more information to make it a cubic. So when it says what conclusion can we make, we can just make that we don't have enough information. We've got enough information for a quadratic, but not enough information for a cubic. So that's why we couldn't find the values of A, B, C, and D. All right, so to investigate this further, choose any 3 intersections with the x-axis for the cubic. Write the equation of the cubic using the factor form of a cubic. Okay, so here is your cubic in factor form, where B, C, and D are your x-intercepts, and find the positions of the turning point. So explain your results. All right, so you're choosing what your x-intercepts are. All right, so we can have -4, 0, 0, 0, and 4, 0. So when we substitute them in to the, I'm going to let A equal 1. All right, so when we substitute them into the cubic, we get AX times x plus 4 times x minus 4. And when we, factorize that, so it becomes a difference of perfect squares. So x plus 4 times x minus 4 factorizes to x squared minus 16. And then you get x cubed minus 16x. But all this you could do on your calculator anyway. So your gradient function, so the purpose of, expanding it is so we could take the derivative. So your gradient function is 3x squared minus 16. So your derivative your x value when your derivative is equal to 0, you get x equals plus or minus 4 on root 3. So you could solve that by hand quite easily. You're just letting this equal 0 and then 16 over the other side, divided by 3, and then take the square root. All right, so what we can conclude is the turning points are not halfway between the x-intercepts, but are symmetrical in this case. All right, so I don't think they necessarily for a cubic have to be symmetrical. So try one more case. What could you infer from these results? So if we let A equal 2, so before we let A equal 1. All right, so I'll just go down. You can keep the same x-intercepts. Just missed a bracket there. All right, but because A is now equal to 2, so here it's 2, not 1 as before. Oh, so we get the same x value for the turning points. Independent, so that is independent of what A is equal to. So you could probably assume that any value of A, you would still get the same. What am I talking about? X value for the turning points. Let me just. So what we had before, yeah. All right, so question 4, now investigate the relative positions of the turning points and x-intercepts of a cubic function of the form f of x equals ax minus b times x minus c squared. The x minus c squared means that it is a repeated factor. So your turning point is actually going to be there at C. So if you just think about C on your axis, you're going to have a repeated factor there. So it's going to turn like that. Or if it was a negative, it would be the other way around. All right, so choose some x-intercepts. So we can have -4, 4, 0, and it's saying let's have the repeated factor at 4, 0. So when we substitute into our cubic, we get this. All right, and then just expanded, we get this, so we can take the derivative. Now you could, I'm just thinking, no, I wouldn't use the product rule because you got A out the front. So actually you could, multiply A into the first bracket and then use the product rule. But remember, you can also use your calculator, so just do it on your calculator. All right, so your derivative, we get 3ax squared minus 8ax minus 16a. So when your derivative is equal to 0, it gives us our turning points. So we get x equals 4 and 4 on 3. So you could just do that on your calculator. So again, x values of stationary points are independent of a. So take the general case, blah, blah, blah. What am I reading here? Okay, so x values of stationary points are independent of a. So take general case, f of x equals a times x minus b times x minus c squared. So if we were to expand that, we get this in terms of a, b, and c. Solve for f dash x equals 0, and we get this. So that means you can substitute any values for b and c, and you'd get your x coordinate of the turning point. All right, so other turning, okay, so your repeated factor of x, value of x, is your turning point, which is what we knew. Okay, so if we go back up here, we knew we'd have a repeated factor at x equals 4, okay, or 4, 0. So that's why we got this one here. All right, so other turning point is predictable and dependent on x-intercept values, i.e. x equals 2b plus c on 3, where intercepts are b0 and c0. So your your x-intercepts, we just substitute them in, and we should get the other x turning point. All right, and then that's the end. So I'm sorry to rush through that. I'll also upload the solutions, but sometimes when you look at the solutions, it's a bit easier to have them explained to you. But if you have any questions, please make sure you do ask. Thanks. Bye.